Okay, that's the second part of our lecture 6, and we are going to talk about kernel ridge. Okay? So we're going to talk about kernel ridge regression and the kernel trick. The reference is our book on chapter 12. So we saw in the previous block that we can consider an approximation function to a general nonlinear function that's a sum of basis functions. Okay, and basically we can write this function, okay, in vector form, and it will be linear, right? We can define the vector x as just stack my h functions here, and we have a linear model where we can estimate this beta by OLS, for instance, if jt is less than t. Okay? And the estimator is the one that's given on the slide, is this one here. Okay? So it's basically a linear regression on nonlinear features. We are transforming our variables into nonlinear transformation of our variables in these functions h, and we are applying OLS. Okay? But of course we can do ridge. We can basically estimate this by ridge, especially when j is large. Okay? And there is a nice way to write the model that's basically rewriting these that way, and it's going to be clear why this is nice. These two forms are totally equivalent, okay? And now consider a new point x and the nonlinear transformation of this point, that's both h of x. We can write the ridge fit for this new point using this expression here, okay, for the beta ridge. That will be h of x transpose xj transpose times the remaining. So we are going to call this xj transpose a kernel matrix, and this lowercase h transpose xj the kernel vector. Okay? And this kernel matrix has a typical element that's given by the function h at point I and the function h at point j. Okay? So we can define the ridge fit just in terms of the kernel matrix and the kernel vector, and the kernel vector is also defined in terms of elements of the kernel matrix, but when one of the terms is just this new point lowercase x. Okay? So look at that we do not explicitly estimate beta and compute the nonlinear features h. We just have to define the kernel. So we only need to be able to compute the kernel of two vectors u and v. Okay? This is called the kernel trick. And why is that? Because in some cases it's much easier to specify the kernel than to specify the nonlinear transformation. So there is a theorem called the Mercer theorem that says that a continuous symmetric function k of u and v that describes an inner product in some feature space if and only if k is positive definite. So in principle, the theorem is telling us that we do not need to worry about finding the right transformation h directly. We just need to specify the kernel, and the kernel will be the inner product of this function h evaluated at 2 points. Okay? And this function h in this nomenclature is what we call the kernel eigenfunction. So for instance, a kth degree polynomial, the kernel is just 1 plus u transpose v to the power of k. Then there is also the radial basis kernel, that's this exponential of minus gamma L2 norm squared of u minus v, and the Laplace radial basis, there's no square, or neural networks, and so on and so forth. Okay, are just examples of kernels that we can use with the read. So it's very flexible nonlinear form. So from Mercer's theorem, given a kernel that can be expressed as an inner product, we can factorize K to identify the transformation. So for instance, if we have a squared kernel, like this for p equals to 2, this means that we have, when we open this for two vectors u and v, what you have is that the transformation that we're implying is that 1 square root of u1, square root 2 u2, square root 2 u1 times u2, u1 square, u2 square. So while we are talking about that, let's go back to the sieves and the polynomial sieve that we saw in our first block. Recall that I mentioned that, okay, when we have p larger than 1, it starts to get complicated because you have all the cross terms and you have to specify all the cross terms, and then your model starts getting a mess. Okay? Or when you have trigonometric functions, and you have to combine with spline or splines that you have to construct tensor products, how to handle large dimensions. It's a problem. But we can make a trick, and that's the kernel trick. So here, we just specify a kernel. No matter what's the dimension of u and v, our kernel will be 1 plus u transpose v squared. And that's define a polynomial, where it's going, if p equals to 3, you're going to have all possible cross products. You can do the calculus here. Okay, so it's easy. If you want something more complex than a polynomial, you can go into a radial basis function that we're going to much more complex, or radial basis function, Laplace radial basis functions, or neural net, and there are an enormous amount of kernels that are much easier to specify, and you just specify the kernels, and then boom, you have then nonlinearity. And how you estimate this? In fact, you don't need to estimate this as long as you have the kernel. You define the kernel, your fit's given by that expression. Of course, you have to determine lambda. How you determine lambda? The same way as we did before. Okay? We can run cross-validation, or we can look at the trace of this matrix, that the smoothing matrix, and then we are going to have the degrees of freedom, and we can use information criteria. Okay? So it's a very nice trick. It's very, very flexible, okay? And it's easy to use. Okay? So we are going to see that in practice on our midterm. We are going to work with these kernel-rich methods, and I'll be very glad to discuss this issue with you on our Friday session. So thank you very much. Have a great rest of the week, and I see you on Friday.